Okay, so you all know this. We've been using second order central difference pretty much all the way for all the problems that we've solved so far. But sometimes in many scientific applications, we do desire to have higher order approximations. And that desire stems from two issues. First of all, we want better accuracy. So suppose you're doing computations, you've done computations with 41 by 41 mesh. What if we say the error that we're getting for the 41 by 41 mesh is not acceptable? At the same time, we don't have a bigger computer to solve it with a finer mesh. Okay, so that can happen at times, and that is where we want a higher order approximation, which basically gives us the same accuracy as a finer mesh, but with fewer mesh points. Okay, that's the basic idea. And storage is one of the important issues here, because as I said, sometimes you may have a case where you simply cannot refine the mesh anymore. Okay, your computer won't hold it anymore, the amount of memory you need. So that's our motivation for using higher order approximation. And here are some examples where higher order approximations are used traditionally. Direct numerical simulation of turbulent flow. For those of you who may be doing turbulence research, you're familiar with that. They typically use what's called compact differencing schemes of very high order. The reason for that is when you want to resolve all the length scales in a turbulent flow, you typically end up with billions of grid points, not even millions. Okay, and so there is a big motivation for using higher order schemes so that you can reduce the number of mesh points you ultimately end up using. Okay, large eddy simulation of turbulence again follows the same logic. The mesh is so fine that already you have way too many mesh points for simulation of a practical flow problem, and so therefore you want to use higher order approximations. Typically in LES people use fourth or sixth order schemes. Okay, acoustics calculations. Now this is one which is more dictated by the physics. Now we haven't talked about all this in great details, and I don't think we are going to in this class, but if you take courses on CFD, then there is a lot of discussion usually on what's called numerical diffusion and what's called numerical dispersion. Okay, the numerical diffusion comes out of treatment of the advection term, and then the dispersion is basically the third order term. And in acoustics calculations, what happens is you have to get rid of both. If you don't, then what happens is a sound wave which is propagating through the medium essentially gets all fuzzy, and it doesn't even reach where it's supposed to. Okay, so you have to use very high order schemes, numerical diffusion and numerical dispersion. All right, and again, typically higher order, sixth order, fifth order compact differencing schemes are used in this case. Okay, Maxwell's equation, similar logic. Here you're looking at electromagnetic wave propagation instead of acoustic wave propagation. And traditionally the finite element community has been very good at this. They have this what is called HP adaptation, where you either increase the number of mesh points or nodes, or you use higher order elements, approximations, so that you can combine the two depending on what kind of accuracy you need. Okay, in finite difference, finite volume, people have not been so proactive in developing these kinds of schemes, but there are lots of examples where higher order schemes are being used. Okay, any questions? So that's our goal. So far we have used the central order, second order central differencing scheme, and this is what our scheme looks like. So we have the second derivative, which is approximated as that, and this is our leading order error term. You're all familiar with this by this time. This is second order. Okay, so that is why it's a second order scheme. So for simplicity of notation in all the derivation I'm going to do now, this is how we are going to write it. Instead of writing these derivative signs, we are going to use J for nodal index, and then these Roman letters essentially for with superscripts for derivatives. So 2 would indicate second derivative and so on. Okay, so here you can, for example, see instead of the fourth derivative, I'm using right here, the fourth derivative, and then the next term in our error expression is actually the sixth derivative. The fifth one cancels out because of equal mesh spacing on the two sides. Okay, just like the third also cancels out. So this is our truncation error, which has this leading order term that we are familiar with, that one, and then we have this additional term, which is the next term. Okay, so what we really want to do is develop a scheme where this guy is eliminated and we have only that error. So that way we have a fourth order accurate, because you see there's the delta to the fourth. We would have a fourth order accurate scheme rather than a second order accurate scheme. Okay, so delta here denotes delta x for short. Okay, all right, so that's just the explanation of what I mentioned earlier. So we want to get rid of the leading order term, this term, and come up with a scheme that has only delta to the fourth. Okay, that's our goal. So what we are going to do is, now of course one thing you could do is you could extend your stencil. Okay, here perform 4 Taylor series expansions and derive a scheme. That's one way to do it. Okay, but there is a slightly more I would say slightly easier scheme, easier way of doing this, which makes use of actually the central difference formula in a recursive way. Okay, so here is our central difference formula. What we can do is we can write a similar formula for the fourth derivative. Okay, remember that each derivative of phi is like a function. Okay, it's simply a function. So this came out of expansion of a certain function which we called phi, but we could also do the same Taylor series expansions for another function. Let's say we call it g, which is really the second derivative of phi. Okay, so the fact that we are doing Taylor series expansions obviously implies that this function is infinitely differentiable. Okay, otherwise we wouldn't be able to use Taylor series expansions at all. So all we do here is, this is sort of like using the law of induction in mathematics. This gets incremented by 2, and then everything here gets incremented by 2. This gets incremented by 2. Okay, it's kind of like saying I've done the same Taylor series expansions and derivation for, instead of phi double prime. All right, so we now substitute that into our leading order error term, this term. Okay, and that gives us this expression. So we have eliminated the fourth derivative, plugged it in here for our leading order error term, and that gives us that expression. All right, now of course we don't know the second derivative, so we have to eliminate them somehow. So the next task is to eliminate these guys from that expression. But you see, once we eliminate these guys, okay, or express them in terms of phi, then basically our leading order error term will be just that, which is what we want, right? So what we do is we again go back to our finite difference formula for the second derivative, central difference, and we now write that for, not for the node j, but also for j minus 1 and j plus 1. And all that takes is shifting the index by 1. Notice that here the central node is j, here the central node is j minus 1, and then you have a j minus 2 and a j, and then here the central node is j plus 1, and you have a j and j plus 2 on the two sides. Okay, so the same formula we are using, just shifted the nodes by 1. All right. So now we can take that and derive an expression for this guy, which is basically what we had right here. Okay, so I'm trying to derive an expression for that guy, and that comes out to be this expression. Okay, this is sort of like extending the stencil. You can see now you have a j plus 2, a j minus 2 in addition to the central core that we have been using so far. Okay, so now I plug that in, I get this expression. Okay, and now sadly enough we still have the fourth derivatives floating around, okay, with a delta square in front of it, so we need to eliminate that also. And here is how that is done. So this is the expression that I showed you on the previous page. Okay, now I'm going to eliminate the fourth derivatives. Again, using the central difference formula, start with that. Use the same idea for the fourth derivative, okay, or for the sixth derivative, this guy. Okay, so earlier we had used it for the fourth derivative, now we are using it for the sixth derivative, and we rearrange that. Okay, and that gives us basically this term, which is what we are interested in, which shows up in this equation. Okay, so we are rearranging this to derive this guy in terms of the sixth derivative and the eighth derivative. Right, so we plug that, we take that and plug it in here, and what you end up getting is something that looks like that, and then if you gather all the terms, this is what you end up getting. Okay, so now here's our new truncation error, which has the sixth derivative as the leading term and then also an eighth derivative term, which is the second term. Okay, earlier we had fourth and sixth, now we have sixth and eighth. Okay, so, and here is the central difference formula, but now this is fourth order CD, not second order CD anymore. Okay, it's still central difference because we are using equal number of nodes on the right and the left. Okay, we have j plus 1, j minus 1, j plus 2, j minus 2, all of those guys showing up. Okay, any questions? I know I kind of went through the derivation in a bit of a hurry, but you can go through it slowly, step by step, and the equations are numbered, and anywhere I substitute anything, I have numbered the equations. So it should be, for example, like that. So it should be pretty easy to follow what's being substituted into what. Okay. All right. So that's our central difference formula now. Now, what we are going to do now is, let's say we now take the Poisson equation that you've been solving, for example, for your homework, okay, and we now plug in the central difference formula. So this is what we end up getting. These two terms, this one and that one, they're extra because of the higher order approximation. Okay. One nice thing is you can write a central difference code and then you can put a clause saying if higher order, then add such and such terms to my diagonals and off diagonals. So in other words, you assemble the matrix for the standard central difference first, and then you say if higher order, then make these modifications to the diagonals and off diagonals. It's like a switch. Okay, you don't have to have a separate code to do this. For example, here you can see this is typically your diagonal, that guy and that guy. Okay, and now you have this 6 over delta x square times negative 1 over 12 being added to your diagonal. Okay, so it makes things pretty easy to code in if you use these kinds of schemes. Okay, now there are some problems, of course. We'll get to that in a moment. So in the general form, we can write this equation as this. So where we have the diagonal, and then these are the two bands right next to the diagonal, the I plus 1 and I minus 1. Then you would have, let's see, this one and that one, they were your far away diagonals, north and south, okay? But these 4 are all extra. If you want to set it up in matrix form, you now have 9 bands, okay, instead of 5 bands, because obviously you've extended your stencil by 2 points in each direction. Okay, you've gone I plus 2 and I minus 2 in the x direction, so that gave you 2 extra bands, and then you've gone j plus 2 and j minus 2 in the y direction, that gave you 2 other bands. Okay. So if I wanted to write down my coefficients, this is what the net coefficients would look like, each one of them. Okay, that's just a summary of the coefficients, if you're interested. Okay, and this is what the matrix would look like. The blue ones, the blue diagonals correspond to the inner core that you've been using, and then the red nodes here, which are extensions of your stencil, correspond to the red diagonals. Okay, notice that instead of having 3 diagonals now clustered in the middle, I have 5 diagonals clustered in the middle, and that corresponds to these 5 points. Okay, and then when I move n spaces away, I hit the blue diagonal, which is this guy. Then I move n spaces this way, I hit this guy. Okay, I move further n spaces, I hit the red diagonal, and I move further n spaces this way, I hit this guy. Okay, so the 2 faraway diagonals are both n spaces away from the central diagonal. Okay, n plus n basically. All right. So now the question is, how do we solve this? I mean, you, for example, are using the ADI method and the Stone's method. So question is, okay, if we use higher order approximation, how do we handle this in the context of those solvers? Okay, and there are several ways to do that. I'll just talk a little bit about Gauss Seidel and ADI. So one of the things you also will, before we move to solvers, let's talk about boundary conditions a little bit. One of the problems that we run into in using higher order approximations are these extensions. Okay, clearly if you have boundary conditions, okay, so here's your mesh, let's say this is, let's say, a boundary. So you have a node here, you have a node here, you have a node here. If you have Dirichlet boundary conditions like the homework problem that you're solving, this node you don't need to solve for essentially. You just set the diagonal to 1 and the source term to the boundary condition, and you're done. Okay, now then we get to this one. This is your first interior node. Okay, first interior node typically would have I minus 1, okay, which is that value, and no problem, we have that value. But now you hit I minus 2, so what do you do with that? Which means that this equation, this interior node equation, you can't even apply to this node, even though it is actually an interior node, because your stencil has extended by 2. Okay, so these interior node equations would be valid from here onwards. Okay, this one you have to do special treatment. All right. So that's one of the big problems. Now, I mentioned a lot of applications where higher order schemes are used. Typically, for all of those applications, it is very common to use symmetry boundary conditions or periodic boundary conditions. Okay. For example, when people do DNS of turbulence, the boundary condition, so basically they do DNS in a cubical control volume or box. Okay, and the boundary conditions on all faces of that cube are periodic boundary conditions. Okay, a lot of times for LES, if it's not wall bounded flows, that's exactly what you do. So acoustics calculations, same idea. So one of the things that happens when you do that is you can use these symmetry conditions, okay, to simplify the problem. So really, because of symmetry, you can say, okay, I minus 2 is the same as I plus 2, and I plus 1 is the same as I minus 1, and you just substitute those in here, and basically instead of having a node with two halves, you're basically looking at one half. Okay, simplifies the equations considerably, and you can basically use the interior node equations everywhere. Okay, in that case, becomes considerably easier. But when you have a real wall or a boundary which is not symmetric, that's when you run into problems. Okay. Now, one thing that is very special about the central difference scheme, now even though we don't really realize it often or don't appreciate it that much, is that in the central difference scheme we are using two Taylor series approximations, and the third derivative, okay, fortuitously cancels out, and we get an error which is second order accurate. Okay. Now suppose I did the same thing. So remember, central difference, we are using two Taylor series expansions, total of two Taylor series expansions, one forward, one backward. Okay. But let's say we are at a wall and we say, okay, we are again going to do two Taylor series expansions, just like we did for the interior cells or interior nodes, and let's see what we get. Okay. So you do two Taylor series expansions, okay, one this about that and the other this about that. As you can see, this is already extending the stencil by 2. Okay. But when I go through my derivation and I derive an expression for d square phi dx square, it is only first order accurate. It's not second order accurate anymore. For the interior nodes, when we did one forward and one backward, we got lucky because this term canceled out. Okay, and the next leading order term came into play, which was delta x squared. But now if you do Taylor series expansions where the grid spacings are basically different, delta x and 2 delta x, you don't get that. You just get first order accuracy. What does that mean? That means that even if I were to extend my stencil further, okay, so suppose I keep adding points here, okay, I use one more point here, one more point here. By the time I get to this here, my accuracy is going to be delta x cubed, not delta x to the 4th, which is what I'm getting for my interior nodes. Okay, so with interior nodes, 4 Taylor series expansions is giving me a 4th order accurate scheme. Okay, but for a boundary node, if I use 4 Taylor series expansions, I'm only going to get a 3rd order accurate scheme. Not to mention the complexity of deriving it. Okay, so that's one of the big problems in using these higher order schemes when you get to the boundaries, because the advantage of using equal grid spacing that we have for the interior nodes, it's destroyed by the fact that now essentially you are using unequal grid spacing. Okay. All right, so what people typically do is once they get to the boundary node, they simply replace it by a second order approximation. Okay, so basic idea is that this equation you are going to use until this point, but when you get here, you just throw away these higher order terms. You revert back to second order accuracy. Okay. Now one might say, well, is that good? Is that bad? Obviously, it's not as good as we might desire, but that's a big plus in terms of implementation, and that's what people go with the assumption that, okay, at least we are getting better accuracy in the interior nodes. And I'll show you an example of what happens when you do that. Okay. Okay, so that's what I'm basically saying here, that the reduction in order is bad, and therefore for the sake of convenience it is common practice to revert back to second order, because even if we try to do a higher order expansion at the boundary, it's not very helpful, because as I said, with 4 expansions you'll still get third order accuracy. Okay. So here are some strategies for solving the system of equations. So let's talk about Gauss Seidel, which is point by point. Basically no change in algorithm except you include the extra terms. That's it. Okay, so your update formula simply becomes that. Okay, this is pretty straightforward. Nothing fancy. Again, by the time you get to I equal to 1 and I equal to n minus 1, or j equal to 1 and j equal to m minus 1, you're getting back to your second order central difference scheme. So your stencil will not extend beyond the boundary anyway. All right. For the other nodes, you simply use this formula. Let's talk about line by line. If you do ADI, okay, so suppose you want to implement this in what you're doing now for your homework. How would you do it? Okay, there are two ways of doing it. One is to use what's called a pentadiagonal ADI solver, and the other is your traditional tridiagonal solver. So if you use pentadiagonal, what you do is you keep 5 terms on the left hand side implicit. Those 5 correspond to, so suppose you're doing row-wise sweeps, it would be those 5 nodes, and then anything to the north or south, those guys get transposed to the right hand side. Okay, now these 5, the contribution of those 5 nodes are, let me go back to that picture here, are all clustered in the middle. So this is called a pentadiagonal solver, in which you have 5 bands clustered in the middle. Okay, these are again very cheap to use and easy to implement because it doesn't require a full Gaussian elimination. All right, so instead of the tridiagonal solver that you had where you have D, A and C, you will have D, A, C, E and F, 5 diagonals. Okay, and it requires a few more floating point operations because instead of 1 elimination you now have to do 2 eliminations. Okay, but that's about it. So very easy to extend the algorithm to a pentadiagonal solver, and people often use that for higher order schemes. So it's called a pentadiagonal ADI. Okay, so basically you're doing row-wise sweeps and column-wise sweeps just like you have been doing so far, except that you now have a pentadiagonal solver. Okay, and that same pentadiagonal solver, by the way, can also be used for those boundary nodes, because essentially the equation's reduced to tridiagonal, but tridiagonal is a subset of pentadiagonal essentially. Okay, with zeros in the extra 2 diagonals. The other approach is to go back and use your tridiagonal solver again, but now you also have to transpose these terms over to the right hand side, okay, which will obviously make your solver much less implicit, okay, because really you're not treating the whole row implicitly anymore. All right. So the pentadiagonal ADI is the preferred one because obviously it's more implicit and gives you better convergence. Okay. Any questions on that? All right. Now suppose you want to use Stone's method for this. Again, you can use a similar approach where all the extra terms that you got, you transpose over to the right hand side and basically make it part of your Q. Okay, and then you use the Stone's iteration as is, but again it's going to be less implicit than the system that you're solving currently, and so it will take a lot more iterations. Okay. Okay, so before I move on, let me just, I said I'll show you an example of what happens when you use higher order schemes. Okay, so here's a very simple example. This example solves the equation, let's see if I can go up a little bit. It's not in here, but I'll just write it down. It's basically your homework problem 1. Okay, solves that equation with S phi equal to e to the power x. Okay, and boundary conditions of, I think, 0 and 1. So phi of 0 is equal to 0 and phi of 1 is equal to 1. Okay, and this is the analytical solution. And what I'm showing here is, let me see if I can make this screen a little bigger so you can see the numbers. So with very coarse mesh, 5 nodes and 9 nodes, okay? So we can really look at the impact on accuracy. So what you see here are percentage errors. This is second order central difference, okay? This is the numerical solution, this is the analytical solution, and then here you have fourth order central difference, okay? There and there. Now, this guy and this guy actually used second order central difference because they are the ones right next to the boundaries, okay? The only node in this case that used a fourth order approximation is this guy, the middle one, okay? But you can already see, even with one node treated with a higher order approximation, you look at the error here, it's 0.10, here it's 0.06, okay? And that effect of having a higher accuracy here propagates also to these nodes, even though they have second order approximation. So they are also more accurate than what you have here, these numbers, 0.07 and 0.08. Okay. Now by the time you get to 9 nodes, of course, a bigger core is actually using the central difference approximation or the fourth order approximation, and you see these results are almost an order more accurate than these. Okay, 1 extra 0 almost. Okay, so this is the effect of using higher order schemes. And if I now go back to what I said earlier about, okay, why do people want to use higher order scheme? The reason is very simple. You can see here that whatever accuracy I'm getting here with central difference, I'm getting pretty much the same accuracy, same level of accuracy, at least order of magnitude wise, with the fourth order central difference, half the number of nodes. Okay, so that's the reason people want to use these higher order schemes. Any questions? So yes, you going back to central difference at the boundaries, or second order central difference at the boundaries, is an issue because boundary conditions are difficult to treat with the extension of the stencil. But even with that approximation, this has a payoff. Okay. Now, in reality, of course, the boundary nodes would be maybe 5% of the total number of nodes in a big computation. Okay. So you have to understand that 95% of the nodes are still going to have higher order approximation, which is nice. And you may have very strong gradients in certain regions inside the computational domain. And that's where this will really pay off. Okay. Any questions?